So let's remember what we did up to now. And actually, this is one of the most interesting topics of this lecture. Uh, well, we did a review of 301 with some extensions so that we have sufficient tools to analyze what we design. Also, we extended some of our findings, like, for example, when we eliminate theta 1,3 from loop closure equations, we could convert it into so-called Freudenstein's equation, which was one of the very rare equations that was linear in terms of link lengths. So we could use it to design or to synthesize a 4-bar to correlate the crank angles for 3 different positions, or by utilizing what was the name? Chebyshev theorem. Actually, we could approximate a function quite easily without doing any elegant optimization. Then we spent some time on 2-position synthesis, which was, I guess, quite easy. But what was, or the important points, the take-home messages were, number 1, Schall theorem, which states that we can move a body from position number 1 to 2 by a simple rotation around the pole. So if possible, we could place a hinge, which is the simplest solution, to the pole to rotate it from position number 1 to 2. This was simple, but it wasn't possible all the times. And actually, it wasn't possible for the first problem in the midterm exam 1 as well. The pole was far away. Of course, my intention was the door was opening like this, but there was no sign for that. So some of you took it like this, that sort of opening. That's okay, no trouble, since I didn't specify it. If you have shown that you can put a revolute joint there, that's okay. I also asked to design a 4-bar. If you did it, no trouble, okay? But in many of the cases, that hinge was not a feasible solution. In that case, we know how to select the moving and fixed pivots. And actually, one implied important result was the number of free parameters we can use to design a linkage mechanism, like a 4-bar slider crank, double slider, or even 6-link, is limited. So actually, there is no way that, for example, we can generate a continuous function exactly, which won't be the case for cams, since we had a continuous surface, as we will see at the very end. Or we can't go like 9 positions or 100 positions. We will see that the limit is 5, and even 5 has some problems, as we will see later. So the number of design parameters is limited. However, for example, for 2 positions, the design parameters were quite many. So we have a better chance to satisfy other design criteria, like, for example, limited location of moving pivots or fixed pivots, or even maybe if they're in a small range, we can satisfy both, because there are too many, I shouldn't say too many, but quite many free parameters. Also, we had seen how to determine the pole analytically, which actually forms a good basis for analytical design procedures as well, in addition to graphical ones. Then we started discussing three-position synthesis, and actually the first topic was utilization of Freudenstein's equation. Since it was linear, it was very easy to apply, and with the help of Chebyshev spacing, actually we could design or we could correlate the crank angles. Then we discussed graphical synthesis, and once you select a homologous point, three positions of it define a circle uniquely, whose center is defined uniquely, so it was trivial. However, this time we have three poles. In two-position synthesis, we had a single pole, which was P12, but for three-position synthesis, we had three poles, P12, P23, and P13. And if the body is not making a fixed axis rotation, these three poles form a pole triangle. If it makes fixed axis rotation, then of course, all three poles would be coincident, which would be a very special case. But for the general case, we have the pole triangle. And we also had an image pole triangle, which is actually position of a pole at a position which is not included in the indices. For example, P13, what is not included in the indices is 2, so superscript in parentheses 2 is position of the pole or location of this pole in position 2, okay? And we find image poles by reflecting the pole about the side that has this, I would say, common index, which is 2. So image poles are mirror images of the real poles about that side of the pole triangle. These were important, but we haven't seen how to utilize them in three-position synthesis. Actually, these were preparations for four-position synthesis. And graphically, actually, if you would like to do the design, it was quite straightforward. Either you select the homologous point, its three positions define the circle uniquely, you find the center. But if you would like to select the center point because its location may be limited, like it should be there or within a box, within an area, then we would utilize kinematic inversion, and we can select the center point, which is the circle point of the inverted motion, and apply the same procedure. So it was straightforward. What was interesting was the analytic approach, actually, the dyad formulation of Erdmann and Sandor, which we will generalize to 4 and 5 positions as well. And it had various forms. The direct form had a W and a Z, where W was from fixed pivot to the moving pivot, and Z was the vector from moving pivot to the representative point on the plane. And actually, this equation shows how many free parameters we have, and we can go up to how many points. So this 5 position synthesis is actually the limitation. If you try to write it for 6 positions, you would have more equations than unknowns, which can't be solved, okay, as we will see later. So in analytic part, Erdmann and Sandor's dyad formulation was very useful, which could be modified for an additional vector R that points from the moving point or representative point on the plane directly to the fixed pivot as well. So you can utilize that if you would like to select fixed pivot without using kinematic inversion as well. Or you can ask 3 positions of a homologous point to be along a straight line as well. In that case, you can have a slider guidance. So these were the uses of dyad equation or Erdmann and Sandor's formulation. And you have the 3-position synthesis homework. Although time is quite long and you have only 5 questions, I would recommend you to start it as early as possible, because we are going to use those concepts in today's topic, and we will continue discussing 4-position synthesis. Why is this interesting? We have to pick such points on the moving plane so that its 4 homologous locations should be on a circle. Now for 3, it was trivial. You could select any 3 points because any 3 points define a circle. But when you ask for 4 points, any 4 points may not be on a circle. So we have to pick such points that 4 positions should be on a circle. That's why it's interesting. And this leads to also 5-position synthesis, okay? And actually 4-position synthesis was first solved by Burmester, and it's called Burmester's theory because of that, I would say, contribution, okay? So let's start with 4-position synthesis. Let's see, or let's start the treatment. So like the 2- and 3-position synthesis, we have geometric and analytic treatment of the problem. Both are interesting. Both have their own advantages and disadvantages. Of course, historically, Burmester solved this problem graphically or by geometric treatment. So you have 1, 2, 3, 4 positions of a plane, which can be represented either by 2 points like A1, B1 in position number 1. So when you move it to 2, it becomes A2, B2. In 3, A3, B3. In 4, A4, B4. Or in analytic treatment, well, if you like, you can use ABs as well, but our formulation would be based on a position vector relative to a convenient fixed reference frame plus an orientation. So once you know coordinates of A's and B's in 4 positions, you can obtain those, or from Z's and Phi's, you can obtain, if you know, say, or if you select an A1, it's A2, A3, A4. So they are dependent, okay? But in geometric treatment, it's more convenient if you know 2 homologous points. And in analytic treatment, if you know the position vectors or sometimes displacement vectors. So for example, Z2 minus Z1 would be delta 2, the displacement from here to there. Okay, so these are all dependent. Once you define the 4 positions uniquely, switching from one to the other is just a matter of mathematics. So we will utilize both representations, but in geometric treatment, as I said, we would use the homologous points. Now, as I keep saying, if you select an arbitrary homologous point on the moving plane, its 4 positions won't be on a circle. So we have to select those points in a specific manner. So not all the points on the moving plane would satisfy this. And I think it's rather trivial, okay? 4 points in general do not define a circle, but under certain specific conditions, they may be on a circle. And we will start showing this first geometrically. Before that, let's discuss the poles. If we have 4 positions, we will have 6 poles this time. P12, P13, P14, P23, P24, and P34, okay? So these are the poles. In 3 positions, we had a pole triangle. Now we have 6 poles, but we will not need to use all 6, as we will see. Now, there is a definition. Sometimes it's called opposite, sometimes it's called complementary poles. Now, this is 2 pole pairs with no common index, like, for example, P12 and P34. And it's just a pair. And you see there is no common index. Or, for example, P14 and P23. Again, no common index. Or P13 and P24. So that's a definition, okay? Opposite or complementary poles that we are going to use. Then we will have so-called an opposite or complementary pole quadrilateral. And actually we have 3 of them. So what happens is you pick any 2 of those 3 pairs and form a quadrilateral, okay? Using 2 pairs of complementary poles, you form a complementary or opposite pole quadrilateral. Like, for example, if you pick these 2, this is a quadrilateral, okay? These 2 do not have any common, those 2 do not have any common. However, as you see, 4s are common here. 1s are common there. 2s are common there, etc. That's why I have a semicolon here, columns here. So these 2 are a complementary pole. Those 2 are a complementary pole, and I combine the 2 to form a quadrilateral. Is this clear? That's very important because this is what we will be basing our graphical construction. Or, for example, you can pick this and that, and it forms this, okay? This is this. This is the last one. Or you could pick the second and the third. You see, that's another complementary pole quadrilateral. And actually, you can use any one of those, okay? So is this clear, the complementary or opposite pole quadrilaterals? You have 3 opposite or complementary pole pairs. You pick any 2 of those and form a quadrilateral. Clear? Any questions? I just see one face. The other bright eyes are hidden, so I don't know if you are with me, if you could follow what I'm discussing or not. I'm not sure. Any questions? Among 42 pairs of bright eyes, I could only see one pair. Too bad. Any questions? Okay, then let me proceed. I'm going to pick one of those complementary pole quadrilaterals. It is sufficient. So actually, whichever is suitable, you can use it, okay? So the discussion is valid for any one of those three, whichever you like, okay? So these were my pole quadrilaterals, and I'm picking the first one. Say these are the locations. So this is P12. The trouble is, I hope you can read them. My screen is too small, plus it is shared, so I can't read it from here. Let me read it from there. So here I have P12. Here I have P14. So if you like these two, and as you see, the common index is 1. So what I'm doing is I'm labeling this side of the pole quadrilateral as side 1, which is very similar to pole triangle. Remember, in a pole triangle as well, we were labeling the sides with the index that was common to the poles. And why is this important? When I need to find image poles, I'm going to reflect them about this side so that they would become superscript 1. That is, the poles that do not have a subscript 1 will assume that position in the position that is that side. For our specific case, for example, if I need to find the positions of these poles, which do not have any 1 in them, in position 1, I will reflect it about this side, okay? Similar to that, for example, this was 1, 2, this is 2, 3, so it is side 2, and this is 2, 3, this is 3, 4, so that becomes side 3. This is 3, 4, this is 1, 4, this is side 4. And as you see, the quadrilateral is warped, if you like. So I'm not using those sides, which would make a proper quadrilateral, but I'm using those sides because what happens is, actually, this is 1, 2, this is what, 3, 4. These two are a complementary pole pair, okay? So I won't have a side here. And these two are a complementary pole pair, so I don't have a side there. But depending on the positions, it might not be warped as well. In that case, those red dashed lines would be diagonals, okay? So whether it's warped or not doesn't matter. It's not a trouble. What I do is I just show the complementary pole pairs by red dashed lines. If it's not warped, these will be the diagonals and we will have these sides there. Or if it's warped, then these are not the sides of the quadrilateral. They don't become diagonals this time. And we have this, okay? Is this clear? So it's not a problem that the pole quadrilateral is warped, or it's not. But we don't connect the complementary poles, but we form the sides by using the common indices. Okay? Any questions? Well, before starting the image or the image pole quadrilateral, let's have our 5 minutes break. I just have 3 minutes. It won't finish in 3 minutes. So let's have our break. After the break, I will start with that and then we will proceed. So we are going to discuss image opposite or image complementary pole quadrilateral. And actually, this is the poles in position number 1. So what we do is we just check the superscripts. For example, this is between 1 and 2. It has an index 1. So in between positions 1 and 2, its position does not change. But this is pole 3, 4. So it's a fixed point or it's a coincident point for positions 3 and 4. And it doesn't have a 1 in it. So in position 1, its location becomes this, or its location on the moving plane is this, okay? Similarly, this is 1, 4. So in position 1, it's in its original location, but this doesn't have an index 1. So on the moving plane, its location is here. And how do we find them? We take side 1 and mirror these poles like this, okay? So it's similar to pole triangle. In pole triangle as well, for example, if you have pole 2, 3, and if you would like to determine its location in position 1, you were taking its mirror image with respect to side 1. That's why labeling the sides are important. If you would like to find the image pole quadrilateral in position 1, the ones that have an index 1, they preserve their locations, but these ones you have to reflect with respect to side 1 so that you find their positions in 1, so that you can form an image pole quadrilateral, if you like, or image opposite or complementary pole quadrilateral in position 1, which we will see how it's going to be used later, okay? But before that, I will discuss the geometric principles that 4 points lie on a circle, okay? Then we will come to this. So let's keep this in mind. We have the opposite or complementary pole quadrilateral and image opposite or complementary pole quadrilateral in any position. I selected 1. All my discussions will be based on position 1, but whatever I tell can be done on 2, 3, or 4, whichever is suitable for you. But also let me stress this out. Position number 1 is an arbitrary position. That is, you may call what I call 1 as 4 as well, okay? The mathematics, the mechanism, it doesn't know it. The only thing is, in some design problems, you may want the positions to be achieved in order. That is, you may want the plane to move from 1 to 2, then to 3, then to 4. Okay, in that case, if order is important, then numbering becomes important. Otherwise, it's fully arbitrary. Whatever I call 1, you may call 2, 3, or 4 as well. So what I tell for position 1 is true for all others as well, okay? So now let's keep the opposite or complementary pole quadrilateral and image opposite or complementary pole quadrilateral in any position in mind, which we will return back later, which will be very useful in Burmister's theory. But let's discuss the condition for 4 points. For our case, they are homologous points on a circle. Now, if we select a chord, for our case, it is the chord A12, okay, which is this. But you could select any other chord, okay, well, since we have 4 points, I have selected 1 and 2 as the chord. So if you have a third point, actually, the 3 will define a circle, no trouble, it can be anywhere. But if we have 4 points, then the remaining 2 points should see the same angle on the same chord, okay? That's the geometric condition. If these 2 angles are the same, then 4 points define a circle. Of course, you can select, rather than 1 and 2, 2 and 3 as your chord, then this would be your chord. Then this angle and that angle, no. This would be the chord. So for this one, yeah, it would be, no, I'm sorry, I just mixed it up. But whatever the case, if you select 2 points as the chord, the other 2 should see the same angle. So if you change it, it would be the same. So you have just a single condition, okay? So for my case, the chord is A2, A1, or you could select it as A1, A2, but what is important is the direction of the angle, how you measure it, okay? That's also important. So unlike ordinary trigonometry, angles have senses as well. And you see A2, A1, A2, A1 in my angle, and in one, it is A3 is the corner, in the other A4. So A2, A2, A3, A1 is a 30 point, I can't read it, 306 degrees counterclockwise rotation. Same is true here, A2, A4, A1. Okay, again, it is the same angle in the same sense. So the senses are important. That's why this order is important, the leg order. I choose A2, A1, or if I had chosen A1, A2, it would be 30.380 what? 6 clockwise it would be, okay? The senses are important. So that's the only condition for these 4 points to be on a circle. Now, Burmister actually did something marvelous. He did all his derivations using bare geometry, but what I'm going to do is I will use complex numbers to simplify the things a little, because we have that tool, but he did this late 19th century by bare geometry, by bare drafting. So what I'll do is Z sub I is the location of the point with respect to a suitable origin that you select. So what happens is actually relative positions of all points are differences of those vectors. So wherever you select the origin is immaterial, since the relative positions are differences, it's origin independent, okay? So you can select this anywhere you like. So what I'll try to do is I'll try to write this relation using those position vectors. And actually, what I'll do is I don't know those points, okay? I would like to pick them such that the four will be on a circle. So after I formulate my problem based on this known thing, I will say that I don't know where that homologous point is, but I will use the relation I derived to locate it so that its four positions will be on a circle. So that was my relation, okay? And I can write this relation using complex numbers. For the first angle, which is the angle at A3, which is that angle, it is actually argument of the difference of these two complex numbers, Z1 minus Z3, minus argument of Z2 minus Z3. Actually, this, well, let me tell you this first. Argument of a complex number is actually the angle it makes with the real axis. For example, argument of Z1 is this. Or you could say that it is a real number times e to the I theta, so theta is the argument, okay? So this angle becomes argument of Z1 minus Z3 minus argument of Z2 minus Z3. Now I'll try to write this angle, and actually they should be equal. So it's argument Z1 minus Z4 minus argument Z2 minus Z4. Now I will try to write the difference of arguments of two angles using complex number algebra. If I can do that, then I can express this and that as I like. And as you see, this difference becomes actually argument of ratio of these two. Okay? So I can express this angle as argument of that. And similarly, I can apply the same thing to this angle, A2, A4, A1. So it becomes this. Okay, still it's not very handy. What I'm going to do is I will recall this. If we have a complex number over its conjugate, or the ratio of a complex number and its complex conjugate, which is a real number e to the I theta over the same real number e to the minus I theta. Actually, the conjugate is mirror image with respect to the real axis. This becomes e to the I to theta. So what I'm going to do is I will take the ratio of this to its complex conjugate, and I will apply the same to this as well. Now, if I just try to write the expression for the first angle, it becomes this, and actually denominator of the denominator will come to numerator. This denominator and this denominator will be in the denominator, okay? And it will become e to the 2 alpha, where alpha is this angle, also this angle, okay? So it should be the same angle. So similarly, if I apply the same thing for the second angle, this becomes, let's say, beta. So one of those angles is alpha, the other one is beta, but we want them to be the same. That is, alpha should be equal to beta. So this imposes a condition like this, which is actually a relation on the positions of the 4 points, okay? So what this relation says is you should select the homologous points such that its 4 positions should satisfy this complex equation. Remember, for 3 positions, we don't have any restriction. We could select any point. Its 3 homologous positions were defining a unique circle, no trouble. If it were 2 positions, again, we could select them as we like, there is no restriction. And from any 2 points, there passes infinitely many circles whose center is on the perpendicular bisector, okay? So this also gives us some insight about 2 and 3 position synthesis as well. Is this clear? So right now I'm just discussing the philosophical parts of it based on 4 position synthesis. Is this clear? For any 2 points, there passes infinitely many circles so that you can select its center anywhere you like on the perpendicular bisector of the 2 points. For 3 points, the circle is unique with a unique center, but if you want them to be, if you want 4 points to be on a circle, then it's not arbitrary. If you select arbitrary 4 points, 3 of those, any 3 of those will define a circle. The 4th may not be on the circle. For the 4 to be on a circle, you should select that point such that it satisfies this complex equation or something equivalent to that, okay? I just derived this based on, I select a chord here defined by 2 points, and the remaining 2 should see the same angle on that chord so that they're on a circle. So the point should be selected such that its 4 homologous positions should satisfy this equation. Any questions up to here? Is everything clear? I don't see any faces at all. Any questions? Okay, if no, then let me proceed. Now, this equation in this form is still not something that's very useful if we don't know the points, okay? Just remember, this is a vector equation, or if you like, it's 2 scalar equations, but how many unknowns do we have? Quite many. And we are given the 4 positions which are defined by the poles. So with this form, the equation is okay, but it's not usable. Let's return back to 2 positions. We had the pole, location of the pole on the moving plane, which was like this, A2 minus A1, where those A's were complex numbers pointing to the representative points, which can be our Z's as well, if you like. And e to the I phi 1 was the orientation in the first position, e to the I phi 2 orientation in the second position, and we were just shorthanding them as E2 minus E1, okay? Similar to A2, A1, E1, E2. And by using this, we just derived the location of the pole on the fixed plane like this. So these are the long notations with e to the i's. And actually, these poles define the motion between positions 1 and 2 uniquely, okay? The location of the pole. So, we've had this expression. Zj, where j is any position, is aj plus z e to the I phi j, or in a shorthand notation, it's aj plus lowercase z e j, where j is the position. Then I will try to write difference of 2 vectors, say j minus ck. So it's like, for example, z1 minus z2 or z3 minus z4, etc. in our equations. So if I have just a direct substitution, this is aj zej. Remember, z does not depend on the position. Why? Because it's the location of the homologous point on the moving plane. The moving plane has its coordinates and the point. So wherever it moves, the position of the point in the moving coordinate system is constant. So it doesn't change. It just rotates with respect to the fixed coordinate system, and the origin of the moving coordinate system moves, okay? So that's why we have such a relation, remember. So it's just direct substitution. I have this minus ak plus ze to the zek, okay? So if I just simplify this, this is what I'll going to get. And if I rearrange this equation, what I'm going to get will be something like this. Zj minus zk is going to be ej minus ek. So when I multiply this with z, I'll obtain this term. And then I have aj minus ak over ej minus ek multiplied with this. These two will cancel. So I'll recover this. Okay? Well, I'm just doing it this way because this is going to become the location of the pole in the moving coordinate system with a minus sign. Remember, it was ak minus aj over ej minus ek, or just aj minus ak over ek minus ej. So that's why I have this minus sign, plus z. So I'm just trying to put it in this form, okay? That's why I did this operation, to recover this as the location of pole JK. Then let's remember another property. E to the negative I theta is 1 over e to the I theta, and a complex number is 1 over its complex conjugate, or you could have the minus here plus there, it doesn't matter, okay? So that's another interesting property of complex numbers. Its complex conjugate is reciprocal of it, okay? So what I'm going to do is, by using this property, I will also write Zj conjugate minus Zk conjugate that I had in my previous equation like this. Okay, so I have this complex conjugate of this is that, reciprocal of it, Pjk, there should be a bar here, I'm sorry, and a bar there, which are missing, I'm sorry. The bars are missing. These are complex conjugates as well. This final equation is correct. What I do is I just move this to up by multiplying it. So this is what I'll obtain. So please put the conjugates here, or let me just put them with my pen, which are missing. Where are you? Okay. So I should have a bar here and a bar there. So these are complex conjugates. The final equation is correct. Let me also correct this. Let me take a note on this so that I'll correct it. Slide 11, conjugates. So after these derivations, actually I can obtain this relation Zj over Zj minus Zk over Zj conjugate Zk conjugate. If I take the ratio of these two is negative Ej Ek, Z minus the pole, and Z conjugate minus the pole conjugate. So I will utilize these equations to equate the two angles. So it is, I accept, a long way, but I feel much luckier than Burmester. He was doing all of those by using simple geometry. Time is nearly up. It's nearly the break time. If you have any questions, I'll be glad to answer. If no, we will proceed after our short break. Today you are so silent. So what we will do is, by utilizing this equation, we will set the two angles to be equal so that the four positions of a homologous point would be on a circular path. So this was our condition, the two angles alpha and beta to be equal, so that we have four positions on the circle. And it was like this. And now I have an expression for this ratio, for that ratio, which upon substitution in the previous slide yields something like this, okay? In terms of locations of the poles, and their complex conjugates. And can you see, for example, this is 1, 3, this is 1, 4, this is 2, 4, this is 2, 3. So I have just 4 of the 6 poles, okay? It can be any suitable 4, okay? Just keep this in mind. We have 6 poles, but 4 are sufficient. And can you see that this is 1, 3, this is 2, 4? So what are they? Based on the first thing we have learned today, what are these 2 poles? They don't have any common index, so they are complementary or opposite. And these 2 are similar. You see 2, 3, 1, 4. So this forms one pair, this forms the other. So these 4 forms the pole quadrilateral, okay? So if I simplify this equation, I will obtain so-called circle point, or sometimes it's K-curve because of its German name, Kreispunkt curve, like this, okay? So actually, the homologous points should be on such a curve. I can't select it anywhere on the plane, but it should be selected on a curve. And actually, this is also called Burmister's curve or Burmister's circle point curve. And if you actually further simplify this expression, you can show that it boils down to this. Argument z minus p13, argument z minus p23 is argument z p14, argument z p24. And this leads to Burmister's 2 theorems, which are because of those derivations. So Burmister's first theorem says opposite sides of image pole quadrilateral makes the same angle or an angle with 180-degree difference with a point on the circle point curve. So we will actually use image pole quadrilateral if we want the circle point curve. And actually what happens is the circle point curve moves with the moving plane. So if you take images, say in position 1, you obtain the circle point curve in position 1. If you use the images of 2, then you obtain it in 2. So what happens is something like this. Let me try to explain it. Suppose this is my plane with 4 positions, like in my very first slide, okay? 1, 2, 3, 4, which are defined by 6 poles. So now, if it's in position 1, suppose this is my K curve. Can you see the pencil drawing? So now, if any questions? No? Okay. So if I select any point on this curve, it's a candidate for A1, okay? And when I move it to position 2, the same curve is, say, at K2 and your A is at A2, A3, A4. And mostly what we do is we just draw it in position 1 and select a point on this. Okay, so what we use is the image poles in position 1. Is this clear? But you could do it for 2, 3, or 4 as well if you like, or if it's suitable. Is this clear to everybody? Now, things are getting trickier. We have 4 positions. Some things are moving. Some things, as we will see, are fixed, etc. So is the discussion on circle point curve clear? The theorem may look a little confusing, but we will see how it is used, and it's very straightforward. But what is important is, if you use the image pole quadrilateral in a position, say 1, then you obtain the circle point in the first position. And it moves with the positions because it's on the moving plane, and every point on this curve is a candidate for a circle point because its 4 positions lie on a circle. And the shape of the curve, of course, depends on the 4 positions. When you change any one of the positions, the shape of the curve is going to change. Is this clear? Any questions? I see something on chat. Let me see. Yes, is very good. Okay, if no questions, let me proceed with the second theorem, which tells the center point curve, or points for candidates for fixed locations like A0s. And it is actually just a copy paste of this. You just delete the image and you convert circle to center, or K to M, okay? Opposite sides of pole quadrilateral this time makes the same angle at 80 degrees difference with a point on the center point curve, or the original name Mittelpunkt curve, or it's called M curve or Burmester's M curve. Well, this curve is fixed. Why? Because it tells where the center of the circle is. And actually, what happens when you do kinematic inversion is my question. Any answers by voice, by chat, or any guesses, I would say? What happens in case of kinematic inversion? Nothing? No answer? Well, I'll just let the fixed plane move and fix the moving plane. What happens, do you think? Shall I give you a hint based on Nasrettin Hoca tale? Do you know what Hoca said about his burial after his death? He said, bury me upside down. And of course, people asked why, and he said, kıyamet koptuğunda dünyanın tersi dönecek, o zaman başım yukarı gelir. Just think in terms of this. What is going to happen if I do kinematic inversion? Yes, exactly, Ege. Circle and center points switch the roles. When I fix it in any position, the K curve will become a fixed curve, but M curve is going to move in the opposite sense with the fixed plane, which was fixed but moving. That's true. And of course, in that case, image and pole quadrilaterals will change roles as well. Okay, so as we will see later, now let me tell these fine points right now, then I will also stress out those. But number one, there is a one-to-one correspondence between the points on the circle point curve and center point curve. That is, say you select an A1 on circle point curve. Then there is a single corresponding A0 on the center point curve. Or if you select a point, say B0 on center point curve, there is a unique A1, or if you like A2, A3, A4 on the circle point curve. And you can find these mathematically, but we are engineers. What do we do practically? Either we select the circle point curve, find its, even we don't need 4 homologous positions. If we are sure what we are doing is correct, we can find the other 2 homologous positions and find the center. It should be on M curve, but we don't need to draw it. Or if the restriction is tight on center point, then we draw the center point curve, select a point on it. By kinematic inversion, we find its 2 more positions, find the center in the inverted motion, which will be on K curve, but we don't need it. It will be just invert once again or obtain the original motion. We will have it. Now, if you would like to check what we are doing is correct, actually, rather than trying any 3 positions, we would draw 4 positions, see that it's really on the circle, but on a CAD software, we can use 3 points and pass the circle, find its center, that's all, okay? So we don't draw both, depending on which point we would like to select freely, we either use circle point or center point curve. But mathematically, there is one-to-one correspondence between the points on the circle point curve and on the center point curve. Okay? Know this, I'm not going to show this correspondence. It's not something easy to show, and we don't need it. We will be engineers. We are not scientists to prove those things, which in practice has no use to us, okay? This is just a technical elective. It's not a graduate course that we should prove that sort of thing. So I won't do that, but please know that there is one-to-one correspondence between the points. So any questions up to here? Things were a little theoretical, and I know these statements do not mean too much. How do we apply them geometrically? And also we will use a dyad equation to apply them analytically as well. But do you have any questions? up to here. Things were a little abstract. Now I will move on to application of all of those, and it is, as you will see, quite simple after this point, and it's straightforward. No questions? Okay, then let me proceed. And let me also check my notes. Yeah. Okay, so the geometric application of Burmister's first and second theorems. Actually, this part is for the first theorem, which is for the circle point, and this pink one is for the second theorem, which is for the second theorem. So they are nearly identical, as you might guess, because the theorems were nearly identical. One was using image pole quadrilateral, the other one was using pole quadrilateral, but I just shortened those. Actually, these are, what was the name? It was so long. Opposite, or what was the other thing? I can't remember even right now. It was just the beginning of the lecture. So these are not ordinary pole quadrilaterals, but the ones that we discussed at the beginning, okay? So what we do is, for a circle point, we select any suitable image pole quadrilateral, or for center point, we select that pole quadrilateral. Number two, we select two opposite sides. That is, actually, those sides do not have common indices. No, not common indices. They should have one common index, but the two sides should be opposite. They're not intersecting at a corner. Actually, I'm going to show it on an example, don't worry. Then it says, draw a line through one of the poles that makes an arbitrary angle gamma with the side of the pole quadrilateral. This line intersects with the perpendicular bisector of the same side at a point called capital gamma. Draw another line making equal angle with the opposite side through the pole of that side. This line intersects with the perpendicular bisector of the same side you have selected at gamma prime. So we do the same thing twice for different sides, and gamma and gamma prime make the same angles with the image poles or the regular poles for the center point curve. So this is for circle point, this is for center point. Then we are going to draw two circles, and these circles are sometimes named as pencils of circles, which have centers at gamma and gamma prime, passing through the two respective image poles for the circle point, or poles at the center point. The intersection of these two circles are 2 points on the circle if you use image poles, or center point curve if you use the poles themselves. So the graphical construction procedure is very simple, and actually the 2 points you are going to obtain are two candidates for, if you like, A's, if you use image poles, or if you use the poles themselves, they are the candidates for the center points. And actually, by changing this angle, which is a single parameter, you can obtain the full curve. And using GeoGebra or any other sort of CAD software packages, by defining this parameter as a variable and changing it from either negative 180 to 180 or 0 to 360, you can obtain the full curve. So let's see the application procedure of this geometric thing. So what I'm going to do is I'll just do it for circle point curve. In that case, I will use image poles, but you could do it for center point curve as well. The procedure is identical, except you won't use image poles. So I'm using P12, P23. So I'm sorry, P12, P34 pair, and P14, P23 pair. But for the poles which do not have an index 1, I should find their positions in position 1. So what I do is I take images of these two poles about side 1, which connects P1 to P14. So actually these two should be on that side, mirror image with respect to these two, okay? So the location of the poles here and at the very beginning of the lecture are not the same, so the motion should be different. And rather than those image poles, if you use the poles themselves, then you will obtain the center point. So what I'm going to do is I pick those, and actually what I'm going to obtain is the circle point curve in position 1. Why? Because these images are in position 1. So any point on that curve will be a candidate for A1. Its 4 homologous positions, A2, A3, A4, will lie on a circle. Is this clear? Now, I'm saying too many things which will be very, very important in the application. That's why I keep asking, is it clear? Is it clear? You might think that they are trivial, but really they are not, and it might be very confusing. That's why I'm just proceeding very slowly and just keep asking you, but today there is no response. Now, I think it's a good time to take another 5 minutes break. I just have 4 more minutes for that, but before continuing with the procedure without interruption, let's stop here. Okay, so what we do is we select a suitable pole quadrilateral. If we want for the circle point curve, actually it is the image pole quadrilateral. If we want the center point curve, it's the pole quadrilateral itself. So application procedure for Burmister's theorem is identical except that difference. So in item 1, we just select a suitable pole or image pole quadrilateral. For our example, it's these, and say these are the poles for the given motion. Now it says number 2, select 2 opposite sides. And what I'm doing is I'm selecting side 1 and side 3, which are opposite. And as you see, one of the sides is in the image. It doesn't matter. You could also select this side, which would be 4, or that side, which would be 2. You see, this time it's not warped. but you could select them. However, here there is something important. You have to select those sides as directed line segments. The direction is fully arbitrary. Actually, I just said in the increasing sense, but this is just my preference, okay? You could select this in increasing sense, this in decreasing sense, or vice versa, whatever. But you should also select a sense for both. Both are fully arbitrary, okay? The sense, let me repeat, are fully arbitrary, but you should have the sense. And what I did was just select in the increasing. Why increasing? Well, for this one, 3 is common, from 2 to 4 increasing. For this side, 1 is common, and I'm saying 2 to 4. It's just up to me, okay? You could do anything, but just put arrows to remember you that they are directional, because you're going to do certain things based on the direction you select, okay? Selection is fully arbitrary, but please do select them, okay? So this is how we apply item 2, select 2 opposite sides. And what is important is, for example, I can't select side 1 and side 4 because they're not opposite, okay? Those sides, they may be crossing as well, but if it's warped, but they should be opposite. Is this clear? Any questions? So we choose 2 opposite sides and also 2 directions arbitrarily. Okay, if no questions, let me proceed with number 3, which says, draw a line through one of the poles that makes an angle alpha, which was arbitrary. Well, it was gamma in the previous case. I just changed it, alpha. That's arbitrary, with one of the sides. So now these say things are what I do arbitrarily. So I select this arbitrary angle to be 30 degrees, and I just make the angle with side 1. And as you see, since I have selected this as the directed line, actually the negative or tail of the vector makes the vertex of the angle. And I measure this angle clockwise, okay? These are all important. And I also drove the perpendicular bisector of this side, which is this line, okay? So that line is the perpendicular bisector. This is an arbitrary line, which makes an arbitrary angle, and their intersection gives me point gamma, okay? Is this clear to everybody? I'll repeat the same thing in 4 for this. So the same thing for 4. That's my perpendicular bisector. Again, I'm using the tail of this directed line, and it's making, again, a clockwise angle 30 degrees, and the perpendicular bisector of this side and the 30-degree line intersects at gamma prime, Okay, so I obtain 2 points, one gamma prime, as a result of item 4. Now, what item 5 says, gamma and gamma prime make the same angles with the image poles. So this angle, P231 gamma prime, P34, and P12, even in position 1, it's already there, okay? Gamma, P14 are the same angles, which is a check of my procedure. And these angles I will call beta, okay? They should be identical. Now I'm going to apply 6, which says, draw 2 circles centered at gamma and gamma prime, and those circles should pass through the 2 respective image poles for our case, because we are looking for the circle points. And since this is the perpendicular bisector, actually any circle I draw through this perpendicular bisector is going to pass through these 2 points, okay? Just think the analogy of 2 position synthesis. Say this is A1, this is A2, that's the perpendicular bisector. I can draw any circle whose center is on this line passing through here. But what is important is these angles are equal. I draw 2 circles, one passing through these 2 poles, the other passing through those 2 poles. And the relation between these 2 circles is these angles, which the center makes with the sides, are the same, and they intersect at 2 points. In general, they may not intersect as well for some values of this angle. For example, if this angle is less than a value, which might be 20 degrees or so, one would be like this, the circle would be, no. If this is, I can't imagine right now. If this increases, yeah, the circle size may decrease, they may not intersect. That's not a problem. But in general, they intersect at 2 points. And these 2 points, K and K prime, are 2 points on the circle point curve. That is, these 2 points are 2 candidates for A1 and B1, if you like. Of course, whether they're suitable in terms of other design parameters, etc., is a big question mark, okay? But what can we do? Actually, we can obtain loci of these 2 points based on changing alpha. And actually, this is how 2 points on Burmister's circle point or K curve is obtained. But if you like, we can also obtain, oh, that's the same slide, I'm sorry. We can change alpha by a slider, if you like, in GeoGebra, or by any means using any CAD package. And we can proceed obtaining many pairs of circles, and we can obtain the circle point curve. Actually, after the previous construction, what I did was find the locus of K based on the slider, find the locus of K prime based on this slider, and I'm sure you could see this is pink, this portion is orange, and this is pink again. So these are loci of K prime, and these are loci of K, and it's a continuous curve. So for our case, since we have taken the image pole triangle, not triangle, quadrilateral in position 1, this whole curve is the locus of circle point curve, and you could select your A1 and B1 anywhere on suitable points on this curve. As I said, it moves with the position. So in position 2, it will rotate about P12 by an angle phi12, but we don't need to do those, okay? Once we select 2 points, then we can find the other homologous points in the other 3 positions much easily. So unless you have a mathematical curiosity to see how this curve is moving, you won't need it, okay? You would just find, or you would just select A1, B1 on this curve, find corresponding A2, B2, A3, B3. Actually, this is sufficient. You can find the center, but if you would like to check the procedure is true, you can also find A4, B4. If what you do is correct, all those 4 points will be on a circle whose center would be A0 or B0 respectively. This is practical, okay? So, any questions up to here? So you could apply this procedure for circle or for center point curve, whichever you like. And you can, after determining the poles, you can obtain the curve as you like. You can select the points, and then you have to proceed, which I'm going to discuss in a minute. Any questions up to here? I know this is not something simple. I know this is not something straightforward. So if you have any questions, please feel free to ask before we proceed more. No questions? Everything is very, very clear? Hope so. Okay, actually, right now, I would like to open a little parenthesis, which tells us something which might be practical as well. We have so-called Q points, which are on the circle point curve. So the intersection of points of opposite sides of image pole quadrilateral are points on a circle point curve. So actually, you can try these curves as well. For example, if you use this pole quadrilateral, intersection of side 1 and side 4 is going to give you a Q point, which is Q14, which is on the circle point curve, so that you can use it as a candidate of, say, A1. Or this is side 2, this is side 3. Intersection is going to give you another Q point, which you can try. So there are actually, for a selected pole quadrilateral, you have 2 Q points. In total, actually, you can construct 3 pole quadrilaterals. So you can have 6 Q points if you like, without constructing the Burmister's curves, if you like. Okay, so these are 6 points on Burmister's curve, if you like, which are easier to obtain rather than drawing the pencils of the circles. So that's a shortcut, and that was the parentheses that I would like to open and close. Okay. Now let's continue with the Burmister's curves, and let's discuss the consequences first for the circle point curve, and then I'll discuss the consequences for the center point curve. These are actually, some of those are not new. I keep discussing them, but I would like to keep them in a neat manner. So number 1, the circle point or K curve, or Burmister's K curve obtained is locus of homologous points in the position you use for the image pole quadrilateral, which for our case was 1, whose 4 positions lay on a circle. So I think this is clear. The next one is, there is a corresponding center point, which is the center of those 4 homologous points. And what we will do practically is, when we select the circle point on the moving plane, just by 2 other positions, we describe the circle and we find the center. If you would like to make a check, you can also find its 4th position, see that it's on the circle, which is a verification of what you did is correct. But just other 2 positions and finding the circle and then determining the center is sufficient in an engineering sense. Then what we do is we can form a 4-bar mechanism by selecting 2 appropriate circle points on the circle point curve and then finding their centers. So we form a 4-bar, A0, A1, B1, B0, move it to 2, 3, and 4th positions. But this but or however is important. These are some of the common troubles we may face. Number 1, all 4 positions of the moving plane may not be on the same branch of the mechanism we design. That is, the theory guarantees that the mechanism exists in those 4 positions. However, it has no information or no guarantee that all 4 positions are in the same branch. That is, remember, we were selecting a sign which determines the closure of the mechanism. So not all 4 positions may be on the same closure, okay? The sign may change. In that case, of course, the mechanism will not be able to move to all positions. If you assemble it in the position that is in another branch, it won't move to other positions, or if you assemble it in other positions, then it won't move to that position. So we have to first check the mechanism passes through all 4 positions. Of course, if it's not passing through all 4 positions, there are 2 possibilities. One is really dangerous, which is actually while applying the procedure, which is not very straightforward, you might have done a mistake. In that case, of course, the best check is check if all 4 positions are on a circle whose center is the center that you have designed. If that's true, then it is the branching problem, which is the pain in the neck in all synthesis, including 2 positions as well, okay? You may encounter this trouble in all synthesis problems, but the possibility of occurring this increases as you increase the number of positions. So this is less dangerous in 2 position synthesis, a little more in 3, but even more in 4, okay? You may have 3 positions in one branch and 1 in the other, or it might be 2 in one branch and 2 in the other as well. So this is the major trouble. Then, of course, we have to check the others, like the transmission angle may be poor at some positions. The link length ratios might be inappropriate. Mostly, we don't want the ratio of shortest to longest link to be larger than sometimes 10, sometimes 20, depending on the design, but that's another trouble. Well, if it is dictated by the design, so this may not be a real trouble, but it might be in certain cases. For example, when you rotate the crank, you may want the plane to visit the positions in the desired order, okay? When the crank is rotating, you want position 1, 2, 3, 4 to be visited in order. And it might not be the case. When you rotate the crank, first you see position, I don't know, 1, then 4, 3, 2. That's not too bad, actually. Cyclically, you can have 4, 3, 2, 1, 4, 3, 2, 1, if you like, but it might be the case 1, 3, 2, 4 as well. That might be a trouble. And also you should check other things, like, for example, the plane is not hitting certain restrictions, or in between the positions, it's not doing something inappropriate, which is, again, dictated by the design. Okay, so the design procedure is lengthy, but after that, you have to perform a lengthy checks, which of course depends on your other design constraints, which is not, I would say, the business of this course, but you should be aware. But this is our business, okay? And this is our business. We have to satisfy at least these 3, okay? But the rest, they are dictated by the design. So it's not something straightforward. It's not something simple. You pick 2 points, form the 4-bar, and if you're not very, very lucky, you have to discard it and you have to redesign it. If you find a good solution during the first few trials before the New Year's, just go and buy a lottery, okay? You're very, very lucky. Mostly you won't be that lucky. You have to iterate a lot. Okay? So this is for circle point curve. We also have consequences on center point curve. Some of those are similar, some are not. Now, why do we use center point curve? Because we might want to specify the fixed pivots, that's A0 and B0 rather than AB. Because as you see, like in three-position synthesis, if we select AB, A0, B0 will be determined uniquely. But if the restriction is on A0, B0, rather than trying to search on proper location of A0, B0 by changing AB, we can directly select those, then these will appear at arbitrary locations. Well, what we do is we just select this time the suitable pole quadrilateral rather than image pole quadrilateral, and we just proceed as the circle point curve. So the application procedure, this is actually the same. The application procedure is exactly the same, except we change the image pole quadrilateral with the pole quadrilateral. And also we have Q prime, if you like, points. This time we don't have the image poles, but the poles themselves. So the intersection of the opposite sides will give us the Q prime curves, which are on the center point curve. And then we can discuss the consequences, which are similar to circle point curve. So center point curve is the locus of center of homologous points whose four positions lay on a circle. And in kinematic inversion, actually, the center point curve of the original motion will become the circle point curve of the inverted motion, as we discussed. Well, there's a corresponding circle point whose four homologous points are on a circle in four positions. If you select the center point, that is, if you would like to specify A0 and B0 rather than AB, then you can use kinematic inversion. Then the center point curve of the original motion will start moving in the inverted motion. So the four inverted positions will define a circle whose center will be the circle point of the original motion. But then we have the same troubles as I said. Okay. So to wrap up, actually, what happens is, so actually this is going to guide us to the analytical procedures. We will have similar consequences in analytical case as well. Whether we use circle or center point curve, there is just one free parameter. In graphical construction, it was our arbitrary angle, which is alpha, or initially I called it gamma, which determines the point we select on the curve, whether it's the circle or center point curve. So once this is fixed, everything else would be determined. That is the location of the other point. If we use circle point, the corresponding center, or if it's center point, the corresponding circle. So locus of homologous points whose four positions lie on a circle, or locus of center of those homologous points, we have only one free parameter. And if you like, you can say it is the distance from a suitable origin. So unlike three position synthesis, we can't select the point on a plane, at least one of those, but they should be on a curve, which is a parametric curve. And although we haven't proven this, there is one-to-one correspondence between the points on circle point and center point curves. Okay. Circle point curve is on the moving plane and moves with that plane, whereas the center point curve is on the fixed plane. And finally, this is something we have discussed as well. If we use kinematic inversion, the roles of circle and center point curves change. So in the inverted motion, the circle point curve of the original motion becomes the center point curve of the inverted motion, and center point curve of the original motion becomes the circle point of the inverted motion. So this brings us to the final break. Now I have analytic methods for four-position synthesis, but I don't want to start it this week because we will just have 30 minutes of time to discuss it. So I think we can quit right now. It's a good time. If you have any questions, please feel free to ask.